about the foundations of statistical mechanics. First thing to say is that the sort of engine, the fuel for a lot of the thinking that's gone on over the past century or so about the foundations of statistical mechanics has been issues in particular about what's called the problem of the direction of time. And that'll be a good way to start off. The considerations in a very natural way branch out from that. But I think that's a good way to introduce a lot of the sorts of things that people are puzzled about, a lot of the sorts of things that people wonder about in connection with the foundations of statistical mechanics. And very crudely, the problem of the direction of time comes up like this. As of the end of the 19th century, when the problem was first noticed, so you had a structure of classical physics in place, Newtonian mechanics, maybe Maxwellian electrodynamics as well, and it was a feature of that theory that, well, let me back up a little bit. There's lots of debate that I was very involved in that now looks to me a little boring. There's lots of debate about exactly how to rightly define what it is for a fundamental physical theory to be invariant under time reversal. But the case that there isn't any disagreement about, the case that looks to everybody to be the cleanest, so maybe the case to have in the back of your head when this is being discussed, is the case of sort of the Newtonian mechanics of particles. Okay? So you imagine a Newtonian sort of world, a world whose entire physical content consists of point-like material particles. Each of those particles moves around in accord with F equals ma. Everything else, everything in the world other than particles, tables and chairs and trees and people and buildings and stuff like that, are taken to be arrangements of these particles moving around in accord with the fundamental laws. Put out of your mind for the moment the fact that there aren't actually solutions of the Newtonian mechanical equations of motion that look in a stable way like tables and chairs and peoples and buildings. That's why we needed electrodynamics, that's why we needed quantum mechanics, so on and so forth. Pretend for the moment that that's not the case. So the deal is this. It's as simple as can be to show that any sequence of positions of these particles is a function of time. Okay, any trajectory of such a set of particles that's in accord with the Newtonian equations of motion, that's everywhere in accord with F equals ma, has the feature that the exact same sequence of positions of all the particles taken in reverse is also in accord with F equals ma. So that crudely put, for any process which is allowed by the Newtonian equations of motion, the exact time reversed process is allowed by those equations of motion as well. Or maybe here's even a slightly more vivid way to put it. Suppose you're given the positions of all the particles in the world, plus the intrinsic features of those particles that are relevant to how they're going to move, their mass, their electric charge, so on and so forth. Suppose you're given all those intrinsic features at a certain time, okay, and you're given the information that is the first derivative sort of information about how the positions of those particles are changing as time moves towards some other time of interest. Notice that we haven't said yet whether the other time of interest is in the future of the time where you're given this information, or in the past of the time when you're given this information. What the kind of time reversal invariance that Newtonian mechanics, what the kind of time reversal invariance that Newtonian mechanics possesses entails is something like this, that you can calculate. So here's the situation. We're given the information, we're given the kind of information I just described at some time t. Okay? That is, at t, we're given information about the positions of all these particles and their non-dynamical properties, their masses, their electric charges, so on and so forth. And we're given information about how the positions of the particles are changing as you roll time in the direction of some other time you're interested in, t prime. Now, I've drawn t prime above t here, which by the standard conventions of drawing on blackboards makes it appear as if t prime has a higher value than t, or as if t prime is later than t. You shouldn't think anything like that. T prime is some time other than t, which is separated from t by a fixed time interval, call it L, say, okay? What the kind of time reversal invariance that Newtonian mechanics has entails is that I can, given the information I just described about t, I can calculate the positions of all the particles at t prime without its ever emerging in the course of that calculation whether t prime is in the future of t or in the past of t. Is that clear? Yes? Okay, good. Good.
It'd be,
Yeah.
if you write, when you write t and t prime there,
Yeah.
usually we think of those as given by numbers, and then inevitably t prime will either bigger or lesser. There's no problem there. It's just, if you didn't specify the numbers, but just the separation,
Right.
then there would be nothing in the data which distinguishes the two directions.
Right. But are you saying there would be something inadequate about just specifying the separation?
No, not at all.
Good. No, so that's right. I see. You're just saying, you mean, it's too bad that I gave these names.
No, not so bad. But
Yeah. I agree. Good. Good. Everybody with me here? So you have a particularly vivid, straightforward, transparent, unmistakable kind of time reversal symmetry in the case of Newtonian point mechanics. Any formulation of what it means, any formulation that's likely to pop into your head of what it means to say of the theory that it doesn't make any foundational distinction between, as it were, evolving toward the past and evolving toward the future, is going to be true of a theory like Newtonian point mechanics. For other theories, Maxwellian electromagnetism, quantum mechanics, so on and so forth, things get a little more complicated in a way that I'll allude to in a minute. They don't get more complicated in a way that has any impact on the tension between this observation about Newtonian mechanics and our everyday macroscopic empirical experience of the world, okay? And the thing about our everyday macroscopic empirical experience of the world is, of course, that it's as clear as it could possibly be that it's not the case of that experience, that what it teaches us is that whatever can happen can in the exact same way, or just as easily, or just as naturally, or just as much in accord with the laws or our expectations, or something like that, happen backwards, okay? And it's worth, that is, our everyday macroscopic empirical experience of the world is vividly and unmistakably time-directed, okay? And the basic problem is a problem of how to put these two together. That is, we have these theories like Newtonian mechanics, and the situation, as I said, is similar with Maxwellian electrodynamics, quantum mechanics, quantum field theory, strings, whatever you want. Okay. These theories all have this very vivid time reversal symmetry about them. These, moreover, are supposed to be candidates for the complete and fundamental and exact microphysical theory of the whole world. And yet, there's a sense which it's not an exaggeration to say is as obvious as it could possibly be, okay, in which our everyday macroscopic experience of the world doesn't have this feature. And on the face of it, that seems like a worry about the claim that these things that do have this feature are serious candidates for a fundamental universal theory of nature. It's worth dividing the senses in which our everyday macroscopic experience of the world is time-directed, I think, into at least three categories. There's one category that you might call the time-directedness of the behaviors of sort of prosaic, fairly simple, ordinary garden variety macroscopic physical systems. So, for example, you bring two gases at different temperatures together and their temperatures tend to equilibrate. Or processes, it's never the case that happens in reverse. The two gases which are in thermal contact with one another spontaneously make the differences between their two temperatures larger rather than smaller. There are frictional processes, like the process at room chair, slowly, beginning, it starts out moving quickly, it slows down and eventually stops as a result of its frictional contact with the floor. That never happens in reverse. We never see smoke spontaneously collecting into cigarettes rather than dispersing out of them, so on and so on. Good. So there's this enormous universe of time-directednesses of the behaviors of ordinary physical systems. It's useful to distinguish between that and another kind of time asymmetry, what you might call the epistemic time asymmetry, which has to do with a very obvious fact. We'll say more about exactly what the content of this asymmetry is later on to the past than we do to the future. The kinds of things we find we're able to know about the past, and the methods by which we are able to put ourselves in possession of knowledge about the past are very, very different from the kinds of things we find we're able to know about the future and the methods whereby we're able to come into possession of knowledge about the future. So there is, on the epistemic level, yet another time asymmetry. And there is, at least in the way we ordinarily talk, a third, what you might call a causal time asymmetry. That is, we make our way around in the world with the very, very deep-seated conviction that by acting now, we can affect the future, but not the past. Okay? There's an easy way to dismiss that kind of idea. There's a sort of junior high school way to dismiss the claim that there's that kind of asymmetry by saying something like, anybody who would even say such a thing doesn't understand what physics is telling us about the world in the context of Newtonian mechanics, for example. Everything is deterministic. There isn't any such thing that physics can accommodate, like a notion of our deciding to act now or something like this. This, I think, on a little reflection, isn't a good answer to the question. Yes, the question as it's usually posed, that is on the causal level, might invoke all kinds of notions of agency and so on and so forth, which one has to think a good bit about exactly how to fit into physics. But it seems like it would be crazy to deny that there's something about the way the world is that we're putting our finger on or gesturing towards when we say it's a feature of the world we find ourselves in, that by acting now, we can influence the future, but not the past. Everybody, I don't know how come I'm not being interrupted more. Yeah, Dave.
That's okay, yeah. I was just going to say, I mean, on that first of the three categories, is it worth kind of saying it's not just that we always observe that these things do something in one direction but not another. We've got a whole bunch of regularities governing the way they do this thing. We've got a whole bunch of higher level dynamic laws.
You mean thermodynamics?
Well, for instance,
right.
Or diffusion equations are all
yes.
And all those equations at a higher level are asymmetric equations.
Absolutely right. Absolutely right. That is, it's not only that they do this, but they do it in a sufficiently robust and regular and reliable way that, as David says, we've developed a whole science of the macroscopic to summarize these sorts of behaviors. And these sciences of the macroscopic typically do involve a direction of time, okay? And the question is, if the real exact microscopic science going on underneath everything else is something without such a direction in it, where does this direction come from, okay, when we get to the level of the macroscopic? Anything else?
With that third, the method of which other expecting that our future actions or the actions now will affect future, lost my thought for a second. I'll have to go back to
Okay, sure. Anything else? Okay, good. The vast majority of the intellectual effort that has so far been invested by philosophers and physicists in trying to solve this problem focuses on the tension at the first level, okay? That is the tension between the time reversibility of the proposed microscopic equations of motion and the time directedness of what I was just referring to as sort of ordinary garden variety macroscopic physical phenomena. Okay? Sure.
Could this be, I guess you call it an emergent property of the microscopic that somehow we don't obviously understand? If we know all about the microscopic world, that then the macroscopic world that you derive from that, though it's a different piece. That's some over that and lots of things you're probably going to be talking about.
Right. So the question is, could it be, well, look, if emergent means it's something you could, in some principled sense, derive from the exact microscopic equations of motion, then there's a worry, okay? The microscopic equations of motion simply do not have a direction of time in them, okay? We could formulate what they entail, like in the way that Shelley was suggesting, without assigning numbers to times at all, okay? Just with something like a betweenness relation, or something like that among times. So, no, it's a pretty straightforward logical conclusion that you can play around with that all you want, okay? You're not going to get a time directedness out of it if there's no time direction in there from the word go. Is that a hand? Yes, it is.
So let me, because we'll start the disagreements, I guess.
Okay, although of course there's going to be
a
time especially reserved.
I do want to make a distinction between two worries you might have. Okay? One of which everybody has, and another of which it seems to me is getting a little confounded with maybe some people. The one that everybody has is, as you say, if the physics, in a straightforward way, for every solution, allows physically the time reverse solution. Right? So if glasses can drop and shatter,
right.
If that's physically allowed, then it's physically allowed for broken pieces to reassemble themselves.
Right.
Now, when I state that fact, I state it in explicitly time-directed terms, right? Because I distinguish the case of the glass dropping and breaking from the case of the shards reassembling and jumping up, okay?
Right.
And as I state it, it sounds like, look, these are two different possible physical things that can happen. The physics allows them both to happen. We often see one.
But I disagree with the claim that you need to state it in a way that is.
No, I didn't say, I just said you do. I didn't say you needed to. I said, in
I
fact,
didn't. You
I
did.
I did, and
Yeah.
that's the normal way you do it.
Yeah. Normal, but yeah.
Well, all right, then I will state that.
Right.
Someone like me who actually believes there is a direction,
Right.
will say these are actually two things that both allowed by the laws of physics.
Right.
One often occurs, typically the other never occurs. That's something that needs to be explained. Fine. There's a different claim, which is the one you're trying to push together with this one.
Right.
Which is to say, look, there's just no direction of time at all at a fundamental level. Therefore, and one can easily jump up and do it, that in some sense there seems to be one at a macro level at some time. And this is not a word you use, but a word that many people have used, but Greg recently, an illusion, okay? Now, that is just, the point is, that's just a different claim. It would require different arguments.
Right.
One can believe that the...
One can set up considerable parallelism between the arguments that would come up. But at the bottom, I agree with you.
Oh,
Sure. And this will be, this theme will come up again and again over the course of this week. Good. Yeah,
I'm
so.
going to make a remark related to what you said. I mean, the thing that worries me a little bit is this, not about anything you said in substantively, but just imagining what would somebody maybe who hasn't had a lot of exposure to physics or statistical mechanics, or maybe even somebody who has, make of this, that they would say, gosh, I mean, the most basic thing that I know is the future doesn't exist, the past is finished, and then and of course I can't control the past because it's finished.
Right.
They might worry about how that fits in with the stuff you said,
Right.
but that for them the most obvious thing in the world would be this fact about what.
Absolutely right. Is that it?
So I would imagine such people, if there
Yes.
are any such here,
Yes.
would be really puzzled people.
Good, but there, I agree. I take it that's a good thing. That is, let me propose the following translation of what you said, and you tell me if it's faithful or not. There's a very strong temptation to answer questions like, to put it crudely, why can I remember the past but not the future? Or why is it that by acting now I can affect the future but not the past? By saying something like, I'm not even sure I understand what you're asking. It's the past, after all, okay? That's why I remember it. That's why it's fixed. It's the future, after all. That's why I don't remember it. That's why it's open to my influence. And somebody might respond, and I take it this is the kind of person you're imagining, somebody might respond by saying, I don't even understand the question. It's like asking why bachelors are unmarried males or something. I don't know what to say. That's what they are, okay? I take it it's going to come as a pleasant surprise to such a person that there are at least people who think, no, a substantive question, and moreover, a question that physics is supposed to have an answer for, can be identified there, okay? It may take a little time just to show the person what the form of such a question could even be, okay? And hopefully we'll be doing some of that here. But so, yes, I agree with you that it's easy to imagine somebody responding like that. And if somebody were to respond like that, I guess what I'd say at this juncture is wait a half an hour and there'll be more to say that I think may shed some light about how questions like that could even constitute genuine questions with content in the first place. Sure. Yeah.
I can imagine also that somebody might say there are ways that just as we can plan for the future or take action now to affect the future, there are also ways in which the future can affect the present. Okay, here's a perfect example. If you apply to grad school, you apply to half a dozen grad schools. You don't know if you're going to be accepted. You don't know where you're going to be accepted. You get one acceptance, and suddenly that determines how you're going to get your airplane ticket, when you're going to go, or how much you're going to pack, whether it's, you know, in the north or the south, etc. So suddenly there's a defined point in the future that hasn't happened yet, but it's affecting your actions.
Well, but let's see. I mean, that sounds like a sort of colorful or metaphorical way to put it. I'm not sure if it's a literal way to put it. That is, one might say it's the information that I've received in the present or the immediate past about what college has accepted me, which is also an event in the immediate past. So that if one were to follow it out carefully, I take it one could reconstruct the kind of process you were just describing as exclusively made up of cases in which it's the present or the immediate past that's influencing the future, not the other way around. Right? Yeah.
Yeah. I mean, you can say, you can make that point a bit more directly, right? It's your beliefs, of course, your present beliefs about the future.
That's right.
What you're doing, but if tomorrow an asteroid comes and destroys the Earth and nobody goes to graduate school forever after, that won't have an influence on
That's
what
right.
you're planning right now.
That's right. That's right. That's right. That's right. Yes. Good. Finally, a question from Steve. Good.
Jumping back to the question of the emergence
Yes.
a moment ago,
Yeah.
I'm most familiar with a definition because it's almost exactly the opposite. So an emergent property would be something that explicitly cannot be derived from the microphysics.
Good.
So
Good. Yes. So that's something we're going to want to talk about a lot too. Let me preliminarily put an immediate reaction on the table. You know, as sort of crudely as possible, which would be something like, if you're talking about emergence in that sense, okay, that is, if you're talking about some feature that the world has that doesn't follow from its complete fundamental laws, doesn't follow even in principle, okay, that is not as a matter of our ability to do the calculation or something like that, but doesn't follow even in principle, that just seems like a refutation of the claims that the complete fundamental laws were anything of the sort.
it means you need something else.
Yeah, it means your claim about those being a complete set of fundamental laws are just false, okay? So if somebody says, no, I'm thinking of a case in which X really does constitute the complete set of fundamental laws, but there's something law-like and robust about the way the world is that doesn't, even in any principled sense, follow from them. Then that just sounds like P and not P. Then I don't know what's going on, right? But this is an issue we're going to come back to a lot over the next 3 weeks. Good. Okay. I'm already way behind. Good. But I very much encourage these interruptions. I think they're very helpful. Let's talk a little bit. So as I said, most of the attention of physicists and philosophers, have paid to this issue of the direction of time over the past century or so, has been paid in particular to the first of the three tensions I just described. There's been talk in the literature that if you understood the first tension, you would obviously understand the other two or something like that. I don't think that's right, but there's a lot to say about that. But for whatever reason, it's a fact. I can think of other reasons too. The first tension is, the first tension is much more codified in strict, well-understood laws than the other two are, so on and so forth. There were plenty of good reasons for work to focus mostly on that. Anyway, that is where this work has mostly focused. up until the past 20 years or so. Let's begin with that. In particular, there is this sort of breathtakingly concise and comprehensive summary that was discovered in the 19th century of the sort of time-directednesses of what I was calling ordinary garden variety macroscopic physical processes. And that summary is thermodynamics, and more particularly the second law of thermodynamics. And it's worth saying a little bit about what the content of that law is. So, this is a really interesting episode in the history of physics. You had these guys in the 19th century. I mean, I take it, I should know much more about the history of this than I do. You know, but I take it, among other things, there's some kind of, there are notions of class, of economic class, involved in this part of the history of physics. You had these guys in the 19th century who were trying to build steam engines, okay, and who were trying to build them as efficiently as they could, and who were noticing all sorts of really interesting, really general, really concisely statable regularities in the way that steam engines behave. The kind of physical system you're interested in if you're building a steam engine is a box of gas, okay? And the kinds of variables you're interested in are energy and temperature and pressure and so on and so forth, because it's the pressure that is eventually going to push the piston and run the steam engine. And you notice quickly that how the pressure behaves is intimately tied up with how the temperature behaves and how much energy there is in the gas, and so on and so forth. We'll go into that a little more in just a few minutes. So these guys were paradigmatically interested. The sort of garden variety macroscopic system, which was of paradigmatic interest to these guys, was a box of gas. And couple of things to say right off. Actually, let me back up 1 second. More generally than just about a box of gas, here's something to notice. The sorts of ordinary garden variety physical systems in which these time reversal, in which this directedness of time asserts itself in a very vivid way, are typically systems with a very large number of fundamental physical degrees of freedom. Okay? That is, the model, the exact microscopic model we have of what a gas is, at least nowadays. This wasn't well established at the time when these guys were doing thermodynamics. But now, we take a gas to be a collection of particles, a collection of molecules, a very large, typically, collection of molecules. Gases, as we'll see, behave in a way that is very vividly time-directed. And this is something quite generally true. The ordinary garden variety macroscopic systems that have a vivid time-directedness about their behaviors are typically systems that have very large numbers of fundamental physical degrees of freedom. That's going to be important. That's going to be something we're going to come back to a lot. Okay. The paradigmatic subject of study for these guys was something like the box of gas. And they made observations like this. Here's an early important observation. Punchline of this, well, let me make the observation first. People noticed things, people did experiments like this. You have Here's a box with a gas in it. This wall of the box is movable. It has a stick on it. That is, it's a piston. Okay. Here's the end of the piston. Put the whole thing on a table. People notice things like this. So suppose you have a little pin here that keeps the piston in place while it's in, but you can remove the pin and then the piston can slide. Okay? And the other end of the piston is in contact with a ball, say. Okay? You remove the pin, you find the piston is pushed out by the gas. Okay? The ball starts to move, that is, the kinetic energy of the ball increases. Okay? And you note, if you're careful, that in processes like this, the temperature of the gas always decreases. If you measure the temperature of the gas at the end of this process, you'll find it lower than it was at the beginning of the process. The reverse is also true. If you have the ball rolling in from here, pushes the piston in a certain distance, and then you hold it in place. The ball loses energy. It eventually comes to rest. It loses kinetic energy. And you find that the temperature of the gas in the piston has risen. These kinds of things suggest that maybe the right thing to think about the temperature of a gas is that it's some kind of a measure of the kinetic energy of the particles of which it's composed. Or, excuse me, I'm not talking in thermodynamic quantity. Forget about that for the moment. This suggests that the right thing to think about temperature is that it's some kind of measure of the energy content of the gas. Okay? What I just said implies that it's not just some kind of energy. It's the same kind of energy that was in the ball. It's just distributed among more things. That is, it's kinetic energy of motion. What the guys who were developing thermodynamics in the 19th century thought was that it was probably some other form of energy. But it's some kind of energy because there was thought to be there were thought to be very compelling reasons to believe in some kind of overall conservation of energy. In a situation like this, energy is disappearing out of the ball. The temperature of this is going up. Maybe that's some kind of a symptom of its internal energy going on. And you have a law eventually written down, the first law of thermodynamics, okay, which is just a statement in thermodynamic terms of the conservation of total energy. That is, it's the law that the change in the internal energy of something like a gas, U, is equal to the amount of some quantity called heat, which is a thermodynamic form of energy that it absorbs in the course of a certain process, plus the amount of work, that is force exerted through distance, that's done on it in the course of a certain thermodynamic process. In the case of a process like a ball rolling in, for example, and hitting a piston, there isn't any exchange of heat with anything else. There's just a certain amount of work that is force applied through distance, raises its internal energy. In the case of the piston pushing on the ball, the amount of work that's done on the gas is negative, so that the change in the internal energy of the gas is negative, so on and so forth.
Maybe there shouldn't be a D in front of the W.
You're right. You're absolutely right. The amount of work that's done. Good. Everybody with me? Yeah? Why is everybody so quiet? Okay. Good. The real interest of the laws of thermodynamics, for our purposes here, has more to do with the second of the laws. And that I want to talk about at greater length. First of all, what these guys did was to distinguish in a convenient way between three different levels at which I might want to describe the physical situation of something like a gas. The micro level, what they call the macro or thermodynamic level, and what they call the level of gross constraints. Okay? Roughly for a gas, the distinctions between those are something like this. By describing a gas microscopically, what you're going to mean is actually, before I say that, I'm sorry. I'm going to keep editing myself here. Let me just back up and say something else, which once again will be important to us later on. Here's how a certain dialogue could conceivably go. Somebody says, what's the right way to describe a system like a gas? Suppose that the background of this is that the exact microscopic fundamental theory of the world is, say, Newtonian mechanics. Okay? Somebody says, what's the right way to describe a gas? Person answers, the same way as what's the right way to describe anything. You give the exact positions and velocities of the particle of which the system of interest is composed. That's the correct description of its physical situation. You want to know how it's going to evolve. You plug it in, you plug that information into the equations of motion. You solve them. Those solutions are going to tell you how the system is going to evolve in time. And there's a very obvious temptation under such circumstances, particularly if we're dealing with something like a gas, to say, look, I understand all that, but it's perfectly clear from our everyday experience with gases that there are regularities connecting variables somehow other than those exact microscopic ones. I know things about a gas like if I heat it up, the pressure goes up. If I heat it up enough, the container explodes. Or if I press on it like this, the temperature goes up. Blah, blah, blah. Okay? So there are these relations that I can just see in the world between things like pressure and temperature and volume and energy content and so on and so forth. And whatever is true vis-a-vis the question of how to exactly microscopically describe this system, the comings and goings, the various comings and goings of the microscopic constituents of the system like this clearly conspire, in certain cases, to produce a relatively autonomous science of the macroscopic, okay, that doesn't need to refer explicitly to those microscopic variables at all, okay, that can rather be formulated in macroscopic terms like pressure and temperature and volume and density and so on and so forth. It's precisely this kind of exercise that these guys in the 19th century were involved in. And the thought was it would be a symptom of unbelievable stupidity to think that the right way to approach improving the efficiency of steam engines was to solve the Newtonian mechanical equations of motion for the microscopic constituents of something like a gas. We had other information, robust, reliable, law-like information about how these macro variables were related to one another. That is, we have here, as we have in many, many cases, economics, psychology, all kinds of stuff, some kind of robust science of the macro. We're eventually going to want to know, of course, or we're eventually going to be curious about how it is that the comings and goings of the individual microscopic particles conspire together to make these macro-scientific laws true, okay? But for practical purposes like building a steam engine, the micro description is going to be absolutely the wrong way to approach it, okay? It's a really important discovery about the world, that there are law-like regularities that show up at a whole bunch of different levels, not just the fundamental microscopic level. okay? It's some kind of interesting feature of the laws that are there at the fundamental microscopic level that they support, that they allow for these regularities to show up on all kinds of different levels. But it's clear that there are different levels at which such regularities show up. Thermodynamics is a paradigmatic example of latching on to regularities like those. Okay, anyway. Good. So these guys distinguish between three levels at which you might be able to describe such a system. The micro level, the thermodynamic level, and essentially what you mean by the thermodynamic level in the case of a box of gas like this is something like the temperature and the density and the pressure of the gas expressed as some kind of function of position within the box. Okay? And then a level of gross constraints, of what they call gross constraints, which intuitively meant something like those features of the gas, like the shape of the box, the size of the box, whether a wall is present or not, something like that, that you can easily actually manipulate in a 19th century laboratory, okay, by means of gross mechanical actions like pulling a wall out or pushing it in or so on and so forth, okay? This language turns out to be useful and interesting for the following reason. People begin to distinguish between those thermodynamical processes, okay, which have the feature that if you reversed the sequence of manipulations you perform to the gross constraints, the sequence of thermodynamic states would reverse as well. And those of which that's not the case. Let me give you a simple example. Suppose I have a box of gas with a piston. Here's the gas. Actually, take the pin out. Here's the piston. Here's a set of manipulations of the gross constraints that I could perform. I slowly pull the piston out until it's here. Okay? That, as we've seen, will have several effects on the thermodynamic condition of the gas. Its volume will expand, its temperature will decrease, its pressure will decrease, so on and so forth. And it happens. It can be explicitly confirmed by going and doing the experiment that if I reverse the manipulations I perform to the gross constraints, if I slowly push the piston vertically, okay? And people were interested in of which transformations are going to be reversible and which aren't. Everybody with me? Here's a very important paradigmatic case of an irreversible transformation. You have two boxes of gas. One is hot, one is cold. Okay? The manipulations of the gross constraints consist of bringing them together in space and putting them in thermal contact with one another. We know that the result of that will be an equilibration of between the temperatures of the two gases. Okay? You start at the end of that procedure and separate them in space. It's not the case that one of them is going to get hot and the other is going to get, one of them is going to get hotter and the other is going to get cold. Okay? They're going to stay at the same temperature as they previously were. This is another very important case of an irreversible thermodynamic transformation. And people wanted to be able to characterize in some general way which such transformations are reversible and which aren't. There are two famous 19th century statements of this so-called second law of thermodynamics, one due to Kelvin, the other due to Clausius. I always get them mixed up. I believe that it's the Clausius formulation that says something like, well, take a case like this, which is the sort of case they were focusing on. Say to yourself, all right, what should I say? Let's try this. There can't be any thermodynamic transformation in which heat flows from a colder body to a hotter one. Okay? This has a time directedness in it. It's sort of what we want. It looks like it's true of situations like this. It's obviously false. Somebody tell me why it's obviously false. Suppose somebody proposes as a you just need to say one word. Refrigerator. Good. Refrigerator is a counterexample to such a law. A properly working refrigerator is precisely something that is constantly removing heat from its interior, okay, which is already colder than the environment, and dumping it into the environment. So a refrigerator certainly achieves a flow of heat, a net result which involves a flow of heat from a colder body to a hotter body. Refine it a little bit. Suppose you say, as Clausius did, here's what I mean. Because note, a refrigerator requires a constant input of energy in order to get this done. So Clausius says, here's what I mean. This is the Clausius formulation, right? Is this the anybody know? I think it is the Clausius formulation. You say, there can't be any thermodynamic transformation whose sole thermodynamic result, that is, which has no other thermodynamic consequences in the world, other than the transfer of a certain quantity of heat from a colder body to a hotter body. Okay? It turns out a refrigerator is not an exception to that. Okay? And it turns out that you think as hard as you can, and you can't think of any exceptions to that. Okay? And moreover, and this is where the taste of sort of class seems to me to come into this reasoning in a really cool, refreshing way. So these guys had all these Rube Goldberg kinds of thought experiments, whereby they could show that these simple, innocent-looking statements like the one I just made have consequences which are fantastically more far-reaching than you would have thought. So, for example, take this case. Take this statement of the second law, the Clausius one. No procedure is possible. No transformation is possible, which has as a net result nothing of a thermodynamic nature other than the transfer of heat from a colder body to a hotter body. Okay, take the case of the sliding chair that we just mentioned before. So consider a process like this. Okay? Good. Suppose we'd like to use the Clausius version of the second law to show that the time reverse of a process like that is a process in which a chair spontaneously starts sliding backwards over the floor faster and faster, is impossible. Here's the kind of argument that these guys came up with. It's a really cool argument. They say the following. Let this be on a table. Let it have a long piston that goes out to here. Here's a chair. Okay? Here's the way they reason. Note, to begin with, that when a chair like this slides along a floor, and eventually comes to rest as a result of friction between the chair and the floor. One of the consequences of that, an easily verifiable consequence, is that the floor around where the chair comes to a stop heats up. Okay? The kinetic energy of the chair needs to go somewhere. Total energy is conserved by the first law of thermodynamics. You suspect that if there's nothing moving, the kinetic energy of the chair has probably gone into heat, and you can make measurements which verify that, okay? And show that the floor actually gets hotter as a result of the frictional forces with the chair. Good. So, suppose that the time reverse of a process like that occurred, okay? That is, suppose that there were circumstances in which a hot section of the floor, okay, suddenly organizes all of its energy, feeds feeds it into the chair where it becomes kinetic energy, okay? And the chair starts to move backwards, like this, okay? If such things were possible, then it would be possible to arrange a situation like this. You make sure that the chair's motion is aimed at this end of a piston, okay? The chair will run into the piston will contract the gas, okay? It will raise the temperature of the gas. There's no reason at all why the temperature of the gas, in this sort of example, needs to start out lower than the temperature of the floor in order for this to work, okay? So the net result of such a process would be energy comes out of the floor, okay? The floor cools down, the chair goes like this, the gas heats up. The net thermodynamic result of a process like this would be the transfer of a certain quantity of heat from a cooler body to a hotter body, okay? And it would have no other thermodynamic consequences, therefore it's impossible, okay? So you take an example like a chair, which on the face of it doesn't have anything to do with the kinds of things that seem to be mentioned in the Clausius formulation of the second law. And it turns out that the Clausius formulation does have a lot to say about which such processes are possible and which such processes are impossible. And it turns out, because these guys were so clever, okay, and because they were thinking in this sort of Rube Goldberg mechanical kind of way, that a simple claim like this can plausibly be parlayed not just into a demonstration of the time-directedness of chairs moving along floors, or of the time-directedness of gases expanding to fill their containers irreversibly, but of the entire array of what we were referring to earlier as garden variety, macrophysical time-directednesses. Okay? Now, to do this anything like justice, one would go through a whole bunch of other examples of this derivation. You will be skeptical that the applications are even remotely as wide as I have advertised them. They are. It's an absolutely breathtaking thing, this second law of thermodynamics, especially in this form. Now, there are forms that we're going to talk about in a few minutes, particularly the form involving entropy, which has right on the face of it a more general kind of feel about the way it's formulated. And that's really nice, and that's going to be really useful, and that's the language we're going to be using from now on in these discussions. But it's worth pausing for a minute and allowing oneself to be filled with wonder and admiration at the fact that these statements of the second law, which look like their applicability is confined to a certain special set of physical situations, is in fact much, much, much wider than that. Okay. What did I do with my glasses? Yes.
You had mentioned that that had to do with class and economics. How does that?
Oh, I'm sort of making that up. But the thought was, there are no doubt people in the room who know more about the history of this than I do. But the style of reasoning that you find in thermodynamics in cases like this is very different than the style of reasoning you found in more, gentlemanly hoity-toity theoretical physics, which had to do with writing down differential equations and finding their solutions and so on and so forth. It feels more like the reasoning, I don't know what, of people who work with their hands, like I say, I don't know enough about the history to justify this very well. That's true. Although Clausius was more complicated, wasn't he? And all of this came out of these guys who were building steam engines. But right you are. I shouldn't project my
Einstein
fantasy.
was pretty good at both styles.
What's that?
Einstein
Was good at both styles. Einstein was good at both styles. Yeah, look, I don't want to push this too hard. You know, I was about to say something like, well, Einstein was middle class, but I don't want to push this. I don't want to push this too hard. Yeah.
I mean, just back on physics. And
Yeah.
Just kind of one observation about how thermodynamics gets its power. I was going to think about this in a sense. On the face of it, it looks like awkward restricted, not just because we think of steam engines and gases maybe, but because we're thinking specifically of equilibrium systems and transitions from one equilibrium system to another.
Good.
And I take it the reason why the way you're talking about it you can hardly enough to this level of generality is because we really mean it, damn it, when we say no process.
That's right. That's right. That's right. And given the limited number of examples they had dealt with, the sort of audacity of proposing something like that is breathtaking. And what's amazing is you go and check it, and it turns out to be right, you know. Okay. Good. What else do I want to say about thermodynamics? Here's what else I want to say about thermodynamics. Look, there's another sort of quaint 19th century sounding formulation of the second law due to Kelvin, which is also nicely illustrated by the chair example, which says that it cannot be the case that a quantity of heat is ever extracted from some body all at the same temperature. So you can think of, say, that body as the floor here. After you've waited, once the chair is finished moving, for the floor to equilibrate with itself, so the floor is all at the same temperature. It's impossible, so says Kelvin's formulation, for there to be a process which involves the extraction of a certain quantity of heat from a body that's all at the same temperature, like the floor, in which that heat is turned entirely into kinetic energy, okay, or into work, okay, something which kinetic energy is capable of doing, into mechanical work. Once again, that directly prevents.
You shouldn't say kinetic energy. You mean
You're right,
microscopic.
into work, converted into work, okay? That directly prevents what happens here because the chair eventually raises the temperature of the gas by doing work on it, okay? What we've just seen with the chair example is that the Kelvin formulation, at least in a case like this, can be derived from the Clausius formulation. It can also be shown by a slightly more circuitous kind of argument that the Clausius formulation can be derived from the Kelvin formulation, so they're equivalent to one another. And what it'll be very important for us to know for our future discussions is that there's a third, more modern, much more widely referred to version of the second law that's current now in terms of a thermodynamic quantity that we haven't mentioned yet called the entropy. Okay. Yeah.
Just an interesting footnote to what you said, which is that if you have negative temperatures, then those two formulations are no longer equivalent.
I don't know. I don't think I know what negative temperatures means.
Yes. So if you what negative temperatures are hotter than positive temperatures in quantum mechanics, spin systems.
Right.
And so if you allow for, just as a kind of, if you were wondering about the scope of the equivalence,
Right.
Is it analytic or
Of what to what? You mean of the two, of Clausius and Kelvin?
right?
I see. But wait, I'm just not, give me an intuition about how I'm supposed to understand negative temperature.
I think of, it's been a while since I thought about this, but think of, I guess, a spin system which, you could have all the spins up
Right.
versus all the spins down.
Right.
How does this go?
Yes, the system's more likely to be in a high energy state than a low energy state. You need
What's
high-
more likely to be a high
Let
energy?
me, we're jumping way too far.
Yeah.
In the kind of spin system Craig is like, take a normal system like a box of gas. The more heat you put into it, the more states become available, right?
Right. Whoops, sorry.
Take a spin system
Yeah,
where it's lower energy spin down and higher energy spin up.
yeah,
Right? The maximum number of possible states consistent with the macro state is right in the middle, right? Where
Right.
it's 50 up and down.
Right.
If you push energy into it beyond that, you keep flipping more things up, and at the top there's only one state where they're all.
I see.
So that's a negative temperature
Good.
region, because as you're putting energy in,
Good.
the number of states is going down.
Good,
So then,
good.
as
Good.
Craig says, the negative temperatures are officially higher than the
Good,
number.
good.
That's
Good,
all
thank you.
well.
Good, thank you. Good.
Yeah, so I mean, it's interesting because you often see in textbooks that the two are equivalent.
Good,
And you
good.
might think that they're logically equivalent or rather than all
Good.
physically possible worlds equivalent.
I mean, even just within the context of classical thermodynamics, the equivalence isn't quite logical. That is, you need to be able to avail yourself of all this stuff that's mentioned in these Rube Goldberg scenarios. You can do this with a chair, blah, blah, blah. That is, there's a lot you need to, yeah, it seems to me even in the classical context, the equivalence between them is miles away from strictly logical, okay? You're availing yourself in these Rube Goldberg scenarios of all kinds of stuff about the way things behave in the world that you know are true, okay?
Yeah, I guess that's the point I wanted to make.
Right,
They're not just notational variants.
Good.
Right?
Good, no, that's
Define
absolutely
different
right.
things and-
That's absolutely right. They're physically equivalent, whatever that might mean, within these physical circumstances. Yeah,
Didn't these same steam engine people, weren't they the ones that discovered things like hysteresis and the fact that you couldn't actually get it to do exact reverse? I mean, they were trying to build
Sure.
engines that would.
no, there are phenomena like hysteresis those are important phenomena. They don't prevent you in simple cases like this from reversing the thermodynamic evolution by reversing the manipulation of the gross constraints. That happens. There are other circumstances where things are more complicated, but there certainly are paradigmatic cases where you can do that. True. Yes.
You want to state that Kelvin law normally gets stated with some kind of inner cycle requirement? Otherwise, if you're not careful, just the gas expanding and pushing the piston will count.
So let's see. This is, so what's the statement you're proposing?
Well, the way I normally see it would be, no process that operates in a cycle has the consequence.
Right. You're right. You're absolutely right. That's right. Good. Anyway, let me go to the formulation that's going to be more useful for us. Here's an additional thermodynamic quantity that you can define. Or rather, the way it's usually defined is in terms of its, not in terms of its absolute value for a given state, but in terms of the difference of its values for two states. So here's the idea. We have two possible thermodynamic states of a system, say a box of gas. Okay? In one of those states, say the gas is confined to a small volume. It's uniformly distributed. The distribution is uniform throughout that volume, and there's a certain temperature and pressure throughout the volume. And in another state, it's in a larger volume with different values of temperature and pressure. Good. There is something you can define called the entropy difference between this state and this state. Okay? And the definition of the entropy difference is as follows. Find a reversible route, okay, that takes you from this state to this state. Okay? That is, find some manipulation of gross constraints which has the feature that it's reversible. Okay? So that if you reverse the manipulations that get you from here to here, it gets you right back to here. Everybody with me? Along that reversible route, evaluate, in general by doing an integral or by adding up however many individual steps you need to add up, okay? evaluate the sum over each of the steps of that route, okay, of the amount of heat that's absorbed by the gas during that step, divided by the temperature of the gas during that step. Okay? So you need to divide up the process into steps small enough so that over the course of each one of those steps, the temperature is effectively constant. That may, in certain cases, require you to divide it up into an infinite number of steps, in which case this sum will become an integral. Okay? But anyway, the entropy difference between this state and this state is defined as this. Okay. In order for this to be a coherent definition at all, there needs to be an argument, which there is in the thermodynamic literature, that for any two reversible routes which you could discover between this state and this state, this sum will be the same over those two routes. Okay. There's a nice proof that that's the case. Okay. Good. And now, once you've defined this entropy difference, and then you can define an absolute value of the entropy by arbitrarily choosing some thermodynamic state as the zero, as the case of zero entropy, and then defining the entropy of all kinds of other thermodynamic states in terms of this quantity evaluated over a reversible path between the zero state and the state in question. Okay. In order for this to be reasonable, there has to be, first of all, at least one reversible path available between any two thermodynamic states of the given system, and in cases which will this sum or integral evaluated over one of those reversible paths is the same as its value evaluated over the other one of these reversible paths. Yes.
Can I ask a question about these reversible transformations?
Yes.
So in physics 101, when we do Newtonian mechanics, we assume there's no friction, but this is just an idealization. Is these reversible transformations?
Well, wait. Let's see. There's a couple of things in that statement I don't understand. It better not be the case that you assume that there's no friction, because then what the clever student ought to say is, okay, class is over, because in the world there is friction. If this theory asserts that there's no friction, this theory is false. End of class. So you don't mean there's no friction. You mean in solving certain simple problems in Newtonian mechanics, we often license ourselves to assume that there's no friction.
Okay, maybe friction is a bad analogy.
Okay.
Let's use the word idealization.
Okay.
Are like reversible transformations idealizations which actually don't?
Sure. This language of reversible transformations, once again, the whole spirit of all of this thermodynamic talk, this is a spirit which we're going to reject in a few minutes when we start to consider the thermodynamic underpinning, the statistical mechanical underpinnings of thermodynamics. But for the moment, we're not interested in the microscopic underpinnings. We're looking for regularities among macroscopic features of the world, okay? And in particular, among thermodynamic features of the world. And we've got ourselves, and for the moment, before we start inquiring into its microscopic underpinnings, the thing to sort of wonder at and appreciate is that whatever the hell the microscopic underpinnings are, we've got ourselves a robust, useful, informative, reliable, law-like science of the macro here, okay? Whose truth or falsehood doesn't depend much on exactly the way the macro features supervene on the micro features. Tim, hold on 1 second, because I just see by the look on his face that I'm not answering.
That's what I wanted to add.
Yeah.
You don't see the look on his face.
Here's the question.
Yeah.
Let me just try.
Okay.
As I understood the question, it was this. In fact, there are no irreversible processes.
Correct.
Period.
Correct.
Okay, they just don't exist.
Correct.
There's always at least a little friction. This is an idealization.
Correct.
To which the answer is you just say yes and then you know. Right? But you can reduce friction and you sort of see a limit as you get less and less. And there are things
But
that
it's
other
also,
folks that mean
the only reason I
irreversible, and
didn't,
that's okay.
the only reason I didn't just answer yes is that the statement about there never being any such things, well, I guess you could look at it two ways. I was about to say it's a statement that's informed by some conception of the microscopic underpinnings. But I guess you could also just say, no, it's informed just as much by our everyday experience of the world as these other things are. Okay, there's not that much at stake here. Yes. In fact, there are no such things as perfectly reversible processes. Yeah,
But
that's
here,
true.
do you mean reversible or do you mean quasi-static?
I mean here reversible in the sense that they're very close to one another in this thermodynamic sense that I was referring to. That is, the thermodynamic sense of reversible can be brought back to their original states by a reversal of the manipulation of the gross constraints. Okay? That goes along with quasi-static. That goes along. But I mean, I think, you know, it's already been made clear that I'm not going to, that I ought not present myself as an authority on the history. I think that's the way the thermodynamic guys use the word reversible.
Maybe I'm just a little confused, because suppose I just have, you know, two gases together at different temperatures.
Yes, what you mean by a reversible route? I'm
And
just
then
trying to think
you
if
let
this is
heat
always
flow
true.
from one
Yes.
to the other.
What you mean by a reversible route is a route through quasi-static states.
But this isn't that's all you mean? Because this is certainly not reversible. You're not going to get,
What do you mean?
once the temperature is the same on both sides.
Oh, no, but that's not it. No, so maybe I'm not understanding what you're saying. The case of the equilibration of two gases at different temperature, I think it isn't quasi-static.
It could be quasi-static.
No, then I'm not understanding
I mean,
what you mean by
that's
quasi-static.
when you would compute that the entropy increase is going to be dq over t, integral dq over t in that case. As long as it's,
No, but that would be,
advantage.
no, but that would be, first of all, I don't think that's true. That is, if you compute, that is the way you would usually compute the entropy difference between, well, let me go through some examples. Bring this up again in a few minutes, because I want to go through some examples of computing the entropy. But no, I think I disagree with what you just said. But let's see, maybe I'm not thinking it through. Maybe I'm not thinking it through carefully. Let's take some examples of this, okay? Excuse me, I haven't said the punchline yet. The punchline is that there is a formulation of the second law in terms of the entropy, okay? And the formulation, which once again, given the usual assumptions, is demonstrably equivalent to the Clausius formulation and the Kelvin formulation. Anybody want a reference on thermodynamics, okay? And on the relations between these various formulations of the second law? By far the best thing I've ever seen is a little book by Enrico Fermi from a long time ago called Thermodynamics, which is just spectacularly beautiful and clear. That's by far the best reference. He doesn't talk about statistical mechanics at all, but he talks about all the stuff we've talked about up to now. Really, really beautiful. Okay, good. Anyway, the punchline of all this, the reason we've gone through all this, is that there is a beautifully succinct formulation of the second law in terms of this entropy quantity, okay, which simply states that the entropy of an isolated system can never decrease, okay? It can either stay the same or it can rise, and moreover, the cases where it rises are cases of irreversible transformations. The cases where it stays the same are cases of reversible transformations, okay? And it can never, if the system is isolated, decrease. Let's see how to apply that to some obvious cases. For example, the following transformation is a paradigmatically irreversible transformation. You You've got gas confined to one region of a box. You've got a removable wall here. You remove the wall. You come back a little later. The gas is spread throughout the box. Okay. We know, moreover, that if you were to come back and reinsert the wall, the gas wouldn't collect back all on this side. Okay. So this is a clear case of an irreversible transformation. If the law, if the second law in its entropy formulation is true, it had better turn out to be the case that this state has a higher entropy than this state. Somebody give me an argument that this state has a higher entropy than this state, given the definition of entropy that I just put up. There's a mistake I want somebody to make because everybody makes this mistake. Yeah,
I'm having to make a mistake.
Yeah.
So as the gas expands,
Yeah.
its temperature is going to go down, but
Yeah.
it's isolated, so its heat is going to stay the same.
Let's see. It's isolated, so its heat is going to, so its heat content is going to stay the same.
But the temperature is going to
So this is 0 over that process.
Yeah.
So this is 0. This sum must be 0.
Yeah.
So that means the entropy difference between this and this is 0.
Yeah.
You made a mistake. Good.
Oh, great.
What was your mistake?
I'm not sure. If I know.
Somebody tell him what his mistake was.
Using a reversible.
Good. He didn't, the process over which he evaluated the transition from this to this was not a reversible process between them. It was an irreversible process, okay? What you're supposed to do in order to evaluate the entropy difference is find a reversible way to get from here to here, okay? And then, once you've found a reversible way, evaluate this sum or integral, okay? You know that once you find one reversible way, that integral will have the same value no matter which reversible way you find. Good. Somebody tell me a reversible way to get from here to here. First of all, somebody say, I think you said rightly, what's the temperature difference between this and this, as a matter of fact, if you do the experiment?
It's lower than the.
It's lower here? Because you made another mistake. What's the temperature difference? Yeah. There isn't a temperature difference, okay? There had better not be, because the temperature is a measure of the internal energy of the gas. The gas hasn't exchanged energy with any other systems in the course of spreading out. So the temperature here will actually be the same, okay? Good.
By the way,
With that-
are
with
you
that
sure
help-
that's true beyond an ideal gas, and where you could have?
No, I'm not sure it's true beyond an ideal gas. I'm just taking the following sort of approximation.
Yeah.
I'm using the following code. You withdraw this quickly. You withdraw it quickly enough so that it's not likely to have an effect on the average kinetic energy of any of the particles. You leave the thing alone, okay? For those systems, like the ones we've been considering here, where temperature is a measure of internal energy, obviously the energy is going to be the same. The temperature is going to be the same. Good. Somebody tell me how to evaluate the entropy difference between this and this. Yeah.
Replace your partition by a piston and move it out slowly.
So, right, so here's something. So let's see. You replace the partition by a piston, move it out slowly. When I move it out to here, is that going to give me this thermodynamic state? No, it's not. Why?
You'll lose heat.
The temperature will go down because it will have done work on the piston. So after doing this, we're going to have to put a fire under it a little bit to put some heat back in. That's going to involve a heat input. Okay? That's going to make this thing non-zero. Okay? And that heat input is going to be positive. Okay? In order to evaluate the entropy difference between this and this, is find a reversible path between this and this. And once we've found that reversible path, evaluate this sum or integral over that reversible path. Okay, here's what somebody suggested, well, just pull this out, okay? That'll turn this into this. Actually, on closer examination, it won't turn this into this, because in the transformation we're actually thinking of, this has the same temperature as this. okay? But if we just pull this out, that's going to allow the gas to do work on the piston that'll decrease its temperature, okay? So by just pulling it out, we'll end up with something with the right density and the right volume, but the wrong temperature. The temperature will be too low. In order to complete the transformation from this to this, we need to heat it up, okay? That'll involve a positive value of dQ. Okay. That's why the entropy of this will be higher than the entropy of this thing.
Just a small thing, don't say put a fire under it. Bring it into a contact with a really huge heat valve.
Okay, why don't I want to say put a fire under it?
You said put a fire under the heat valve. Because you want something that can absorb heat back in when you reverse the process.
Oh, no. Oh, I see what you're saying. Okay, in order to make it, no, but no. Oh, I see. Yes. Yes. You're absolutely right. You're absolutely right. Thank you. Good. So, as we would want, okay, this is, after all, a paradigmatically irreversible process. It had therefore better be the case that the entropy of this state turns out to be higher than the entropy of this state. It is. Okay. And once again, if we were doing this properly, if we were doing this in a course, we would spend a week or so going through a lot of similar examples. You'll just have to trust me that it works out very nicely. Okay. And that, moreover, you can eventually, as I said, prove, given the usual assumptions which we were talking about before, prove the equivalence of the entropy formulation with the Clausius formulation and the Kelvin formulation. But the entropy formulation has the advantage of being more transparently, you might say, general than the Clausius and Kelvin formulations, and more transparently generally applicable than you don't have to be smart to figure out all of the implications of the entropy formulation as you do to figure out all of the implications of the Clausius and Kelvin formulation. Yeah, no.
This may be something you want to talk about later, but how do you make sense of entropy differences between states of the whole universe? If you're not going to talk about it, if you can't do it in terms of reversibility, that's going to be easier to talk about, as you said, once we have, first of all, that's never going to be completely easy to talk about. Okay, I mean, there are lots of very active debates to this day, which we'll be talking about, some of which we'll be talking about here, about the question of how to associate an entropy with the universe as a whole. But, that having been said, just very sketchily, I mean, there are going to be all kinds of reasons why the universe is special in terms of assigning an entropy to it. But just crudely speaking, you go along, you do your science, you figure out, you figure out how to assign an entropy to any system, no matter how large it is. Okay. The minute you have the no matter how large it is, the first thing to say to yourself is going to be, what's the problem with assigning an entropy to the whole universe? That is, I guess the question is, is there something that made you raise that question at this juncture? Somebody says, there is a question there, but I'm not sure why you're raising it here. That is, I've presented a way of assigning, oh, I see. What makes you raise the question at this juncture is the idea of gross manipulation. Good. Good, I'm sorry. But look, it turns out to be the case that entropy is an additive phenomenon, okay? The entropy of any pair of systems, of any collection of systems, can be shown to be the sum of the entropies of the subsystems. So in that way, you could still imagine, although you can't although you can't change these gross constraints on the universe as a whole, you can change gross constraints on any parts of it. You have this additivity. What?
Yeah, well, but there might be things which would go way beyond that.
No. There might be things which go wrong.
Your real answer would be, look, this motivated, led us to a deeper understanding of entropy in terms of
statistical mechanics. That's true.
Yeah, but I mean, that is, and once again, there's going to be a problem about assigning the total, energy to the universe or charge to the universe. But that's because of features of geometry, and that's because of more modern stuff. Is it that you think that there's a more obvious problem assigning entropy to the universe than assigning, say, energy or charge or something like that? You know how to assign charge to individual bits of it, you just add them up.
Problem, but,
Say something more
no,
about
it's just, entropy's not, because people are arguing like crazy about entropy. I mean,
That
does suggest that there's a more obvious problem.
I'll certainly accept that. Yeah, David.
I mean, just one thought is that this thermodynamic notion of entropy is only actually defined for systems of equilibrium. So
Right.
big chunks of the universe aren't equilibrium.
That's for sure. Right.
Now, it might very well be that we have an appropriate statistical mechanical generalization that coincides with this thing in equilibrium that's defined off equilibrium.
Right.
But this notion inside
Good.
itself is only in equilibrium.
That's fair enough. I agree. Yes.
In this case, if the larger box is the whole universe, you can't do the last step. You can't immerse it in a larger heap.
Yeah. That's I take it what Noah was saying. I agree. The thought was, sure, you can, but what you can do is do it to individual pieces of it at different times. But I don't want to push this too hard because indeed there is going to be a very involved story which isn't settled yet about what kind of sense it makes to assign an entropy to the universes, for sure. Somebody else had a hand up. Yeah.
So you said this applies to isolated systems. Is there a more precise sense of isolated that you're using?
Energetically isolated. They're not interacting with anything else. They're not exchanging energy with anything else.
So if you had a system where you couldn't define an energy,
Sure. Yes. Sure.
that's what it applies
Sure.
to.
Absolutely. Good. Okay. Good. I wonder if, all right, let's, Shelley, vis-a-vis the question you brought up about, so if I bring, let's just see what the right thing to say about that is. Now I'm curious. So you bring two gases together at different temperatures.
Well, you actually did that over here too, to heat it up.
No, but that's
After the
different.
cooling.
As Tim rightly said, what you want to be taking the heat from here is a large reservoir, okay?
That's right.
Whose thermodynamic state isn't going to be changed by giving heat to this one, okay? That is whose temperature, whose pressure. This is different.
But why is that really relevant? I mean.
Well, here's what my thought was about the two gases of finite size. Okay, so you have a hot one, you have a cold one. Okay, then you allow them to equilibrate.
Yeah.
Okay, good. Here's the way, if you look in Fermi or something like that, here's the way they'll evaluate the entropy difference between the initial and final states. Okay, they'll find a route from the initial state to the equilibrated state. Okay, that involves putting pistons here and drawing them out, okay, and putting this in contact with other pistons and pushing them in quasi-statically, so on and so forth, okay? And then, if you evaluate the sum of dq over t over all those processes, you'll find the end state is higher than...
But what about just the simple process of letting heat slowly flow?
What good does the slow do here? This has lower temperature all the time. So although the heat loss divided by T, you get a positive, and integrate over it, you get a positive number.
Yeah.
That's the thought.
And you have to do it slowly so that at each time you're talking about equilibrium states. So
You mean you're talking about equal temperatures?
uniform temperature
Right,
from the
uniform
two
temperatures
sides.
through each box.
Before to let it come to equilibrium.
So maybe the point is just that, okay? That if you do it slowly enough, it'll be the same as with the pistons. Yeah.
I mean, I think maybe I'm coming in late here, so I just want to go back to it, but maybe we're talking past each other, there's, what you do, and then there's the justification for what you do. So, the way I think of it, you imagine the big state space, with all the different thermodynamic states, and then, you're going to now imagine all these different reversible paths between the two states, and, then you have this proof that number is invariant, under any different path, and then that's a proof that the entropy is a...
No, that's right.
The end state, so then you can just do the end state, so then you don't have to do the, incremental thinking about it.
Yeah, no, that wasn't, I don't think that was what
That's not
Shelley was worried about.
Okay. Like I said, I was not here.
The deal is this, there are two things here coming apart. One is the notion of a reversible path as having the feature that if you reverse the manipulate, so suppose the way you manipulate the gross constraints here is you just happen to have here something that's not too thermally permeable, but enough. Okay, so that if you leave it there for a long time, the temperatures will equilibrate. Okay, so now the deal is the manipulation of the gross constraints that's in question here is just bringing the two boxes together. Okay, in that sense, this is an irreversible process. In that if you separate the two boxes, when the temperature is equal, the temperature won't diverge. Okay, so in that sense, by this definition of reversibility, it's not a reversible process. Okay, you're making a different claim that if if the heat transfer is slow enough so that the process is quasi-static, okay, then the integral of this over this path will have the same value as it has in the sense of manipulation of gross constraints, reversible.
Yeah, so
Yeah.
I'm saying, so I guess the point was that I didn't realize this. So Fermi makes the point that
Right.
if you can do something quasi-statically, you could also do it reversibly in this sense.
No, I mean, I'm not sure what to think about this. It looks like Tim has
Yeah, no, I
something.
mean, I think, this is just clarificatory, because
Right.
I'm just following the discussion. As I understand it, Shelley's thing is you can define the entropy as that integral over any quasi-static path.
Right.
You might have a theorem that every irreversible path is quasi-static.
Yes,
But
not the other way
his
around.
example would say it's actually a much broader, but he's certainly correct that you do often calculate it as he said.
No, wait.
You know.
Every reversible path is quasi-static.
Right.
The question at issue here is whether every quasi-static path qualifies as a reversible
And whether
one.
this integral over every
That's
quasi-static
right.
path will be the
That's
same.
will give the same value.
Right.
That's a good question, which never occurred to me.
I remember in Collins' textbook on thermodynamics, you've looked at textbooks on thermodynamics far more recently than I have, so this
Right.
is 30, 40 years ago.
Right.
But he makes a big difference between reversible processes and
That's a
quasi-static
good
processes.
question. I don't, so the question, you see, the deal is that I'm trying to remember the arguments that this sum is the same over every reversible path. And I'm wondering if those arguments would also apply to a path which is not reversible but quasi-static. And I just have to look at, I just don't know the answer to that.
I
Yeah.
doubt it, because those involve making cycles,
Right.
and the cycles depending on being reversible.
Right, that's right.
Either from A to
Right,
B or
so
B.
it's not,
So
but
I doubt that you can-
so then what are we saying? That it's clear that the integral of dq over t here is positive.
Right.
It's not clear whether it has the same value as in the reversible case. And if it does, it's not clear whether that's a coincidence or that's something deeper. Thank you, Shelley. I don't know. You're quite right that this sum will be positive here. Okay. It's another question whether it'll have the same value as on a
I'm
reversible.
pretty sure it will. You do it the right way, the right sequence.
And then the
asymptotically.
question is, can you make a general argument
I
like
think
that?
that's
Because
the
as
general-
Tim
I
says,
think that's the general statement I've seen, and
well, what's puzzling is that the standard argument does involve
That may
being
be-
able to go in a cycle. Yeah, I don't know. That's a really good question. Yeah.
I mean, I'm pretty sure you can make a reversible path that effectively does that, just by switching out heat balance with infinitesimally smaller.
No, of course. That's what, but Shelley, you can make a reversible path that gets you from here to here. Okay.
Yeah, but I mean, it would do the exact same thing. Lower.
Oh, I see. Well, so I'm not sure what you mean.
So I'm saying take the hot thing on the left
Yes.
and put a heat bath right next to it. That's the same temperature.
Yes.
And then put another heat bath.
Oh,
next
I
to it.
see. So you mean
That's
you can
long.
make a reversible path not only that gets you from here to here, but that gets you every point along the way. But still, it's going to involve other things between those points.
I mean, it's just going to involve large heat baths.
Right.
It won't involve doing anything with the volumes of the boxes. So since you're just removing heat from one and adding heat to the other.
Right.
The
Maybe
calculation's
so.
exactly
Yeah,
the same,
maybe that's-
regardless of whether it's going to be heat bath or just going directly from the hot to the cold.
Maybe that's right. Maybe that's right. Yeah.
So, okay, so the first question is very quick, which is just whether someone can remind me what quasi-static means.
Yes. A quasi-static process is a process that takes you through a sequence of for example, in a case like this, what we mean by thinking of the thing as quasi-static, in a normal case where you bring a hot body and a cold body together, okay, that's going to produce temperature variations even within the hot body and the cold body, okay? That is, it's going to be the parts closer to here that are colder, the parts farther away that remain hotter, so on and so forth, okay? So that instant by instant, the bodies involved by themselves aren't anything that has the form of an equilibrium state for that body. What it means for a process to be quasi-static is for that not to be the case, okay? That's what we mean by quasi-static. You had another question?
Yes, another question is, so again, I think probably just indicates misunderstanding. I'm still not quite totally clear. So in the first case you're doing, so where you let this thing go out and then you stick it into contact with the heat bath and then it warm up. I'm still not 100% clear about why putting it in contact with the heat bath counts as reversible on the Gross constraint.
Oh, so here's the...
Getting heat bath away, it's not going to cool down, right?
No, that's right. Let's see. So you're talking about this case here.
Yeah.
Right, so maybe we don't need a heat bath either. Maybe what we need is a piston. Is that right? Let's figure it out.
I mean, you can make it reversible by starting off with, you just put a heat bath at the top, and that will get it to the temperature you want, and then reverse it, remove the heat bath, and then move the piston back down, and then you put the heat bath back to cool back down. So you just have the heat bath on both sides.
Good.
Restart.
So you could do that. That's right. You could do that, or you could do it with a piston. Right. Good. Good. Thank you. Excellent question. Good. Anything else? I'm now, at least an hour late, I guess finished with what I wanted to say about thermodynamics, and wanted to start to say things which will go on into the afternoon and into tomorrow about statistical mechanics. But anything about the thermodynamics that somebody has a question? Yeah.
It sounds to me like Shelley was kind of applying this thing of treating each box as a separate system, right? And then you might want to say, well, what's the entropy of the overall thing? And then you say, oh, well, you just add up. But if you don't want to assume that entropy is additive, then you should actually come up with some procedure that just involves manipulating. Just think of it as one system and find some way of manipulating it so that it's reversible.
Well, no, I don't understand. All of these derivations very frequently make use of the fact that entropy is additive. Okay. That's perfectly legitimate. Okay. And what you're going to, that is, I'm not even sure how to apply a formula like this, for example, to a situation like this. Oh, I see what you're saying. If you were coming at it with pistons and heat baths and so on and so forth that are outside of the system, then you could evaluate heat flows in and out of the system as a whole.
But the temperature is not well defined.
Right, but the temperature won't be well defined. That's right.
Then
That's
you have
right.
that
No, I don't
science.
see, yeah, actually, I don't see how to apply this formula without breaking these two up into separate systems.
Just have a heat bath outside the system at one temperature.
No, but still, you want to know how much heat this system absorbed at which temperature. The system as a whole, that's what goes into the definition of entropy. System as a whole doesn't have a temperature. You need to break it up into subsystems that do. As far as I can see.
Yeah, that's the standard computation
That's right.
we're doing all the time.
That's
The
right.
difference in temperature is responsible.
That's
for
right. That's right. So no, I'm not sure I see a way of calculating that quantity, without breaking this up into subsystems.
Does that mean you could never prove that entropy is additive?
No, no, you can. So how does the proof go that entropy is additive?
Proof from what?
Yeah, that's a good question. Maybe it's
Distinguish two things you might mean by entropy additive. You might say, I've got two isolated subsystems. Is the entropy of the total of them going to be the
Right.
same as that? That I think is going to be almost definitionally true.
right.
And I think that's what's in the work that you find. The separate claim that if
I
I
think
have a
that's
homogeneous
right.
substance, entropy goes up to the
I
same
think
substance.
that's right.
That's substance. I think there are additional assumptions that you go in.
I think that's
over
right.
there,
I think that's right. I think it is being assumed in cases like this that entropy is additive. Yeah. Yep. Yep. Good. Okay, as it's for the afternoon, but that gives us. I mean, are there more things that people wanted to bring up about what we've talked about so far? No. Okay. Good.